I would just like to welcome you all to our webinar today. This is the 7th Fenix webinar of our webinar series. It's called Introduction to the ICEI Resources at the CEA. And our speaker for today is Thomas Leibovici from the CEA. I'm Nicoleta Chiapidou, member of the dissemination team of the ICEI project, and I'm based at the BSc. And I wanted to let you know that the webinar is being recorded and the full recording is going to be uploaded on our webinars page on the Fenix website soon after the webinar is finished. So we will keep you posted about this and you will receive an email with all the information after the webinar. And the structure of today's webinar is that right after my very short introduction now, Thomas will take over with his technical presentation. He will present his slides, and afterwards we will have a Q&A session, so you will have the opportunity to ask your questions. We prefer that you ask the questions in the chat, so feel free to write questions if you have during the presentation or during the Q&A session at the end. So I will read them out loud, and then Thomas and maybe his colleagues will be happy to reply to your questions. And then in the end, I'm going to conclude the webinar with some final slides with some useful information for you.
So hello everyone, and welcome to this webinar, and thank you for your interest in the Fenix resources installed at CEA, and more precisely in the TGCC Compute Center managed by CEA. So in this webinar, we'll first have a recall of the kind of resources provided by Fenix and how they are implemented at TGCC. Then we'll go into more details in the computational resources and storage systems, their hardware, how to use them. We'll then talk about virtual machine services, and we'll end with other services that we provide to TGCC users to help them running their computations. So we have four kind of systems of Fenix installed at CEA. The first one is an interactive compute cluster, which consists of nodes with GPUs with large to extra large memory. There are two classes of nodes. The goal of this system is to provide a quick access to compute servers to run data analysis and visualization in an interactive manner. You'll see that this system is also usable for HPC simulations, given that it has a low latency network. So it can also be used for classical batch computations. The second kind of system is a virtual machine service. It is implemented as an OpenStack cluster to manage and run virtual machines on which you can run your own image, so you can deploy your own environments in these machines, and this can be used to run services accessible from the internet, basically collaboratories, repositories, website, databases. So it's convenient to develop platform services. The third kind of system is active data repositories. So in the context of Fenix, we provide two spaces for that. The first one is the two file systems are Lustre file systems. One is legacy hard drive disk file system called Work, and the other one is more performant and is made fully of SSDs. It's called Flash. So the purpose of those file systems is to provide working space for large data sets on the compute center. The last kind of system is archival data repository. So we provide two of them. One is also a Lustre file system, but which is more capacitive and with migration to tapes for a larger capacity. And the other one is an object store based on the OpenIO software that is accessible through a Swift interface. So the purpose of those systems is to store data for the long term and possibly sharing this data to outside the compute center, to other sites, or to access them from other places somewhere. So now let's go into the detail of the interactive computing and storage systems. The interactive computing cluster consists of 30 nodes. Each node has two Intel Cascade Lake CPUs, and each CPU is 18 cores at 2.6 gigahertz. They have 384 gigabytes of RAM, one GPU NVIDIA V100 with 32 gigabytes of memory. And two extra nodes in this cluster have a much larger memory, as they have 3 terabytes of memory, which can be convenient to handle large data sets. And these nodes also have 4 CPUs compared to the other who only have 2. All those links are connected through InfiniBand HDR network, which provides low latency and high bandwidth. So this system is totally suitable also for MPI applications. The cluster has an aggregated I/O bandwidth of 150 gigabytes per second to the storage, in particular to the work and flash file systems we'll describe later. So the work file system is a Cluster Stor L300 appliance based on Lustre 2.12. So roughly, it has a 3.5 petabytes capacity and provides a 70 gigabytes per second bandwidth. So this one is only made of hard drive disks. So if in your project with request you don't have particular needs of random IOs, you can have this file system. The other active storage is the flash file system, fully based on SSDs. So it's particularly adapted for intensive IO patterns like data analysis, AI, etc. It's made of DDN controllers, and each controller has 84 SSD drives, large SSD drives. In terms of metadata, it can handle up to 1 billion files. So the total capacity of this system is smaller than the work file system. It's only 970 terabytes, but it has a higher throughput, 120 gigabytes per second. And last but not least, it also has a high rate of operations per second it can handle. It can exceed 1.4 millions of operations per second in read, and 232,000 operations per second in writes. The store file system is for archival, so it's in the class of RRD systems in Fenix to store data sets on the long term. It's a hierarchical storage system, so it has multiple levels of storage. The top level is a Lustre file system, of 4.8 petabytes. And this data is then migrated to tapes, which makes it very extendable. We can extend it up to thousands of petabytes of capacity. This migration between disk and tapes is transparent to user. So you can access this system like any other file system, and the data will be automatically loaded from tape when you access it. And then the data will be migrated back to tapes after a few weeks or months if you no longer use it. Notice that this file system will be also available through a Swift interface in the future. There is currently a development as part of the ICEI R&D to implement a Swift server over Lustre. The other archival system is an object store of 7 petabytes. It has a lower throughput of 15 gigabytes per second. And in terms of metadata, it can handle up to 2.5 billion objects and provides a Swift interface, possibly S3. We must, if there are needs to have an S3 interface, you can request it, and it is possible. The slides are quite dense, and there are a lot of information into them. So I may skip some information. Feel free to ask questions at the end if you want some details on a particular item. Now, how to use the systems and access them. So first, you can find on the Fenix website, there is some documentation to explain you how to request and access to the systems. And Nicoletta will also give you more details at the end of this webinar. So basically, once you have requested some resources, there is a peer review and a technical assessment. And if your resource request is accepted, you are notified. And then the operation team of TGCC will contact you and provide you with all the needed instruction to access the systems. So how this is the big picture on how you can access the interactive compute cluster. So when you connect through SSH, you arrive on login nodes. These login nodes are not here to run the computation by themselves, but from these nodes you can allocate resources on the interactive computing cluster. To access the systems, here is the address, SSH to fenix-aic.ecc.ca.fr. So when you connect to this address, there is actually a load balancing mechanism to ensure the load is fair shared between the login nodes. There is also a mechanism that ensures that all your connections go through the same login node, which may be convenient if you have multiple connections that share the same resource on the login node. Alternatively, you can address each of the login nodes independently using the addresses -log1, -log2 listed on this slide. And through the login nodes, you can also do file transfers using SCP, rsync, SFTP, and so on. When you connect through SSH, you are authenticated by typing login and password. There is no public key authentication. And what else? These login nodes, the hardware of these login nodes are AMD processors. So there are basically from these nodes you can transfer data and submit jobs. A few words about some security rules for connecting to the TGCC and connected from the TGCC to other services. So to connect to the TGCC, you must register a host that follow the following rules. It must be located in a European country. It must have a public DNS record associated to a public fully qualified domain name. And the security officer of your organization must ensure that the host follows the best practices in terms of security. And then you send this information to the TGCC hotline validated by the project lead to register your source host you connect from. To access a service from the compute center, you must follow the same conditions as above, and this can only be done for encrypted flows to authenticated services. So basically, SSH or HTTPS are okay. Now we are going to take a closer look to useful commands and in the user environments. The first one is module. Module provides ready-to-use environments for using a wide range of tools, compilers, libraries, applications. So here is a list of useful module commands. Module avail lists what software is available. Module load makes it possible to load the environments needed to use a given product. You can specify a version. Module list shows you what's currently loaded. So you can take a look at the documentation for all other module commands available. Modules handles dependencies for you. So it's a very convenient way when you need to use software. Toolchains is a set, defines a set of tools built with a given compiler and MPI version, and all this. So the current default toolchain is made of Intel 19 compiler. It will be soon Intel 20. And MPI4 library. So if you take a look at the available toolchains for software, you can type module help. In this example, you can see there are two different toolchains available, one with Intel 19, one with Intel 20. So to select a toolchain, you just have to use a module load command and specify the related string, and then all your tools you'll load after that will follow this toolchain. Available compiler on the system are Intel compiler, and PGI compiler. Here on this slide you have the default and latest versions available on the systems. So compilers can be selected using module. We recommend to use the Intel compiler because it's we build all tools of the environment with this compiler, and we will do most of the non-regression tests using this compiler. So for a support point of view, it's better to use it. Notice that the default version of Intel and PGI compiler will be Intel 20, PGI 20. So if you start a project right now, it's better to already use these versions to avoid a change during your project. A few words about how to allocate resources on the interactive computing cluster. So as I said, the login nodes are not for computing. If you run jobs on the login node, your tasks will be stopped. To allocate an interactive compute node, you have to use a batch manager, which is Slurm on the directory supercomputer. Slurms allow you to submit batch jobs and also to run interactive tasks. We'll have examples in the next couple of slides. You have two, the interactive computing cluster provides two partitions. One is V100L, it's made of the dual socket nodes with 384 gigabytes of RAM, and V100XL for the quad socket nodes with 3 terabytes of RAM. The Slurms manages the priority between jobs, so it takes various parameters into account for this priority. It takes the current rate of resource consumption over the last few weeks, and also compares it with the target consumption given the lifetime of your project. So if you underconsume, you get a higher priority. If you overconsume, you get a lower priority. And we usually advise to have a regular use of the resources along the lifetime of the project to avoid consumption peaks. Because if all users use all their computation resources at the end of the project, everyone wants to use the machine at the same time, and so people are not happy in this case. The billing. So by default, the consumption of a job is based on the number of cores multiplied by the elapsed time of the computation. In this mode, each core is dedicated to a single job. Notice that if you want to use GPU, you need to allocate the full node using the -X or -C option to allocate all cores of the node. And there is a work in progress. We have a work in progress to be able to share GPUs, but it's not currently enabled. Another mode of billing is using the oversubscribe mode. This mode can be convenient for interactive usage. So in this case, the cores of the system are shared between possibly multiple jobs and multiple users. So there can be up to 4 jobs per core. So it's convenient if you have peaks of consumption in an interactive usage. When you have burst of when you need a lot of cores on the machine, you will be able to use many cores, and the rest of the time the compute power is available to other jobs and users. So in this mode, you are billed 1/4 of the core, and by default you have 1/4 of the memory per core available, but you can request more at your job allocation. So this is something quite new, and we just set up, and we will adapt probably this depending on the actual use we state. For the job management, we recommend the use of CCC commands that come from a software suite called Bridge. It's an abstraction layer of the batch system and resource manager, which helps running tasks in the TGCC environment. If you are familiar with Slurm commands, it's very easy to transpose your scripts. So is some example of commands. There are CCCMP info, CMQ info, CMPP for listing available partitions, quality of services, jobs. CCMSCCT for getting information of a job. CCMSU for submitted batch job, and CMP run for running tasks on some allocated resources. Here are more concrete examples on how to allocate resources on the interactive computing cluster. The first example is allocating a node in the extra large partition. We allocate one node, the -n1 option. -x is for an exclusive usage. A -s is to have a share. So it's also opening a share on a dedicated large memory node of the cluster. The second example is allocating 8 cores, opening a shell on 8 cores with another subscription allocation, like I just described. And the third example is allocating 4 cores for 10 hours with X11 forwarding from the first task of the job, which is convenient for visualization. We'll also provide soon GPU accelerated visualization system, which will likely be based on nice DCV. It's a very convenient system for remote visualization because you don't need any specific client application or any plugin. You just need a browser that supports HTML5. Now let's talk about the storage systems. So when you arrive on the TGCC, you have 3 storage areas available. The Scratch file system is a workspace for temporary data. It's purged after 60 days if you don't access the files. The second workspace is work for permanent work data. There is no purge on this file system, but there are quota and there are no backup. So we have 2 of them, the legacy work or the flash file system I described you before. So this will depend on the need of your project. Store for archival data. This one has a high capacity, but it can have a high latency in case your data is on tape. On this system, we recommend to have a very large file over 10 gigabytes, which is more tape friendly. To specify the workspace you want to work in, you have to specify a module switch, default data dir, and your project name, because users can have several projects, can work in several projects, so you have to specify the associated directory. Notice that this command also applies to Swift. So depending on your module switch command, it will place you in a given Swift directory. The access paths of these different file systems are available through environment variables. So for your own personal folders, you have CC scratch dir, CC work dir, CC store dir. And for shared folders for work projects, it's all CC scratch dir, all CC work dir, all CC store dir. This is how to use the Swift object store from the compute center. So when you're on the compute center, I said module switch will select the space where you store the data in Swift. Then you module load Swift. This will define all needed information in your environment to access Swift. And then you can easily access Swift without any other argument for authentication and all of this. Swift list is to list your objects and containers. Swift upload is to push data to the object store. Swift download is to get data from the object store. So this is a command line example, and you have also a large range of languages that provide a Swift client API. So, for example, one of the most common is Python Swift client. Notice that currently you can access this Swift storage from the internet, and this access will be available in November. A few other useful comments. This is CCC quota that represents you the disk usage for your own login, but also for your group. So for each space, you can see the current usage and the current code. CCC My Project is the same for computational resources. So when you use this command, you can see for your current project the number of consumed hours for each login of the project, the total usage, and your allocated compared to the allocation for the whole time of your project. Now the VM service hardware. So this consists of 20 hypervisors to run the user virtual machines. Each hypervisor has 2 CPUs, Intel Cascade Lake of 18 cores. So the whole cluster sums, there are 600 available cores for the user virtual machines. And each hypervisor has 192 gigabytes of RAM. There are 4 storage servers to provide local storage to the virtual machines. So there are 60 terabytes of SSDs available for that. We use Ceph to manage these drives. And there are other service nodes to run OpenStack services, management nodes, and the cluster has a 10 gigabits Ethernet network. The cluster is installed with the latest OpenStack release, just released in September, called U3. So we're in the process of deploying this cluster right now, in configuring the cluster. These are the flavors that we plan to be available. So GPP has small, medium, large, and extra large with a different number of these virtual CPUs, RAM, and disk space. So the VM storage is on SSD. There is an encryption mechanism that makes when your data goes to the network or to the storage, it's encrypted with a user, a key for each user to prevent access from other users. The vCPUs correspond to hyperthreads. And there is no CPU over subscription. So when you request vCPU for your VM, you are dedicated. The CPU are dedicated to your VM. You have no competition with other VMs running on the same cores. Of course, all this has a lot of optimization to make the VM faster as possible on this hardware. So this service will also be available in November. When you are in a VM and you set up services on them, you have the possibility to access other TGCC resources, namely compute resources, filesystems, or archival storage. This is here we can see the way to do this. So to access the compute resources, you can connect through SSH and submit jobs. Here it's a simple example with a CCM subcommand, but you can write scripts in your TGCC home and execute them remotely from the virtual machines. To access the TGCC file system, you can use SSH interface. It's a very convenient way to mount Filesystem remotely, through SSH. So in this example, you log into the Fenix AIC login node, and you want to access your CC work dir from your VM. So you can specify the CC work path and mount it to a local work directory on your VM. And the Swift is available from the internet, so you can also access it from the VMs. To make such a remote access from a VM which is exposed to the internet, it is recommended to not use your own login account, because if there is a secret breach on your VM, the attacker can use your login and go and access your data, your resources and data on the compute center. So it's not recommended. So what we can do for you is create you an account with limited access to the resources of TGCC. For example, if you want to have a read-only access to a given path of work, we can create an account which has a read-only rights on this particular file system, which limit the impact in case of there is a secret incident on the VM. So we end with the set of services we provide to TGCC users. So for example, that the user documentation is only accessible once you have a TGCC account. So this URL will only work if you have already an account on TGCC. It requires a login and password. Also, if you when you connect on the login nodes, you can type machin.info command that will provide you a lot of useful information to use the systems. TGCC has a multi-level support hotline for the users. So you can ask the hotline if you have any question, if you want to manage user account creation, things like that, or even if you have you need for advanced applicative support on the systems. The hotline is available from 8:30 to 5:50 p.m. Central European Time, and they can be contacted through the following mail: hotline.tgcc@ca.fr, or the phone which is written at the bottom of that slide. So we're done. We end this presentation with this nice picture of the Fenix hardware installed at TGCC.
Okay, so Thomas already spoke about how to access the Fenix services, but I'm going to give you a few more details. So first of all, we have the HPP eBrains call specifically for European neuroscientists at large. And this is an ongoing call, and interested people can go on our website and check the details and apply for this one, and there is no deadline. And then there is the Praise ICEI call for proposals, and that's round 3. It opened a few days ago, and the deadline to apply for this is the 15th of October. Again, like the other call, this is for researchers in need of scalable and interactive computing resources, virtual machine services, and active and archival data repositories. Again, all these links will be sent to you tomorrow in the informative email that you will receive after the webinar. So feel free to check all the details on these calls through these links, and also on our website you see the link at the bottom here. We have all the information on how to access our resources. A few words about our upcoming event. So if you're thinking of attending the online Bernstein conference at the end of September, we will be joining two virtual booths there, a Jülich booth and the Human Brain Project one. So again, you can see the details on our website. There is the Fenix online tutorial on the virtual machine services taking place on the 20th of October. This tutorial has a limited number of places available. So at the moment there is one place left, but you can always register in order to be included in the waiting list. So just have a look at that, and we are planning to repeat this again in the future. And finally, there is the eBrains infrastructure training that is taking place in November. If you're interested to have a look at that and participate, and the details can be found on our events page on our website. I would like to thank at this point all the ICEI Fenix partners for making this webinar series possible. And we would really appreciate your feedback for this webinar. So I'm just going to share a link now in the chat. So it will just take you a couple of minutes to reply to the survey. It's just for us to have some feedback on how we're doing with the trainings and the webinars and improve ourselves. And finally, this is my last slide. I just wanted to let you know that we are running a Fenix user forum, which is an online platform for potential Fenix users, current users, and anyone interested in our infrastructure services and resources. You can very easily sign up for this, and you will be able to post your questions in the forum and just exchange experiences in using the Fenix infrastructure and ask us any questions. And of course, if you have questions or doubts, you can email us, and we will be happy to help you also with the Praise ICI call applications. And you can find, as I mentioned, all the details on our website, and follow us on Twitter so that you are updated with our latest events and news. And thank you very much, Thomas, for your presentation today, and for your colleagues for helping us with the Q&A session. And thanks to all of you for attending, of course, and we will be happy to see you in future Fenix events. Thank you very much.
Thank you for organizing. Thank you all for your interest.